Hi everyone, today we're going to be doing modular arithmetic, which is something we can use to solve number theory problems, and is something I quite like to use in my number theory proofs. Okay, so what is modular arithmetic? Modular arithmetic is a language to express number theory problems involving divisibility. Okay, so notation is as follows. We say A is congruent to B mod M. We can also write this as A is congruent to B, and then the mod M at the end of the expression. So how this would be read is A is congruent to B mod M or modulo M. What this would mean is A and B will leave the same remainder when divided by M. So in other words, if we can rewrite A as being equal to mx plus r, and B equal to my plus r, where r is the remainder, x and y are some integers, so r is smaller than m, so there is going to exist some integers x and y such that this is true. So let's quickly look at an example. Say we wanted to look at 53 mod 3. So what is 53? 53 is equal to 3 times 53 is equal to 3 times 17 plus 2. We now see this leaves a remainder of 2. So for 1, this is going to be true. We can also say 11 mod 3. 11 is equal to 3 times 3 plus 2. Once again, a remainder of 2. So this answer is also going to be 2. Since 53 and 11 both leave a remainder of 2 when divided by 3, we can also say that 53 is going to be equal to 11 mod 3. Okay, quickly another example. Say we wanted to know 21 mod 12. So 21 is equal to 12 times 1 plus 9. So 9 would be one of the options to write. Another thing you can note is that you can also say that 21, or let's write the number minus 3 as well. So minus 3 is equal to 12 times minus 1 plus 6. So in other words, plus 9. So in other words, you see once again this also leaves a remainder of 9. So minus 3 is going to be congruent to 9 mod 12. So this is one option of this is true. So you can say, since both of them are going to leave a remainder of 12, we can also say that 21 is going to be congruent to minus 3 mod 12. Yeah. Okay, now we're going to look at some properties. Okay, properties are as follows. If we have A is congruent to B mod M, then this will imply that, or if and only if, A minus B is congruent to 0 mod m. So notice you just subtract b from both sides. Generally, for all integers a, this is going to be true. A is congruent to a mod m. For 3, we have if a is congruent to b mod m, and this also implies that b is going to be congruent to a mod m. So you can switch the terms on both sides. Doesn't matter which side is which. Next, we have that if a is equal to b mod m, congruent to b mod m, and b is congruent to c mod m, and this will mean that a is also going to be congruent to c mod m. So that's kind of what we did at the examples at the top. For the fifth property, if a is congruent to b mod m and c is congruent to d mod m, then this will imply that ak plus cn is going to be congruent to bk plus dn. This is actually plus minus, so you can add or minus on both sides, where k and n are integers. So we can quickly look at an example. Say we had 5 is congruent to 11 mod 6, so this is true. And we have that 7 is congruent to 13 mod 6. So both of these are true. If you divide 5 and 11 by 6, both of them will leave a remainder of 5. If you divide 7 and 13 by 6, both of them will leave a remainder of 1. So we know this is true. So you can see this is kind of being the A, this is the B, this is the C, and this is the D. So now what we're going to say is we can have any two integers k and n. So we can say 5 times 2 plus 7 times 3 is going to be congruent to, once again, 6. So we use the same m. 11 times 2 plus 13 times 3. So what we had now, we had k is being equal to 2, c is equal to 3. So let's see if that works out. On this side we'll have 10 plus 21 congruent to 22 plus 39, so that's 31, and that's 61. So let's divide both of these by 6. So we can rewrite 61 as being 6 times 10 plus 1. 31 is equal to 6 times 5 plus 1. And we see it is true since both of these terms, 31 and 61, leave a remainder of 1 when divided by 6. Okay, now onto the sixth property. Okay, we have that if A is congruent to B mod M and C is congruent to D mod M, then we will have AC is being congruent to BD. So this is kind of similar to that one divisibility rule we had, that divisibility property we had. So you multiply this side by this side, both left-hand sides and both right-hand sides, and this will be true. Okay. Now for number 7, if A is congruent to B mod M, and n, or let's say n is a natural number, then we have that a to the power of n is going to be congruent to b to the power of n mod m. So once again, like that, almost as if it is a divisibility rule, we can make both sides to the power of something. Okay, now for the 8th property. If A b, and d divides m, so d is a factor of m, and d is bigger than 0, so d is a natural number. Then we have that a is going to be congruent to b mod d as well. So then a and b are going to be congruent mod m, and they are going to be congruent mod d. Okay. Then we have that minus r is congruent to m minus r. So kind of like the example we had at the top, minus 3 is congruent to 12, 12 minus 3, minus 3, this side is going to be equal to 9. So you can, in other words, you can use negative numbers as well, and you can rewrite negative numbers as positive numbers using modular arithmetic. Okay, so let's quickly look at a problem involving this. So let's say we wanted to know the last two digits of 1999 to the power of 2021. Okay, so firstly, what does the last two digits mean? The last two digits of any number is just going to be the number itself when then divided by 100. So say we had 153. So 153, if we divide that by 100, we're going to get 1 plus 53 over 100. Or we can say 153 is going to be equal to 100 times 1 plus 53. We could have the number 26538 is equal to 100 times 265 plus 38. So what I mean to say is, when we say the last two digits of a number, what we mean is we want to know what that number will be mod 100. So last two digits, in other words, we want to know what this will be mod 100. So let's do the question. 1999. Let's just look at 1999. So 1999 mod 100 is going to be equal to minus 1. Why is this true? So if we look at the last property, we had that minus r is congruent to m, and then m minus r. So what we have here now is going to be minus 1, m, so m is 100, and then 100 minus 1, this is 99. We can also add on this side, so we can add a multiple of 100, that is how we get to 1999 is equal to minus 1 mod 100, since 99, 99, these correspond. Then we have that 1999 to the power of 2021 is going to be congruent to minus 1 to the power of 2021. Now if we look at minus 1, so minus 1 to the power of 1 is just equal to minus 1. Minus 1 to the power of 2 is 1. Minus 1 to the power of 3 is minus 1. So next one will be minus 1 to the power of 4. It's going to be equal to 1. So you see the minus 1, 1, minus 1, 1. These will continue. So every second number is going to be 1. Every odd number is going to be minus 1. So 2021 is odd, which means that you can rewrite this as being minus 1. So this side is going to be equal to minus 1. And since we have that minus 1 is also congruent to 99, so we take it from here. This means that we can say that 1999 to the power of 2021 is also going to be congruent to 99 mod 100, which means that the last two digits will be 99. Last two digits. Okay, let's do another problem. Okay, so we have the following problem. Prove that if m and n are positive integers, such that seven divides m squared plus n squared, and so if this is true, then we must show that 7 divides m and 7 divides n. Okay, so let's look at different numbers and different cases of numbers and see what we can deduce from their remainders when they are divided by 7. We can rewrite the statements as being, so we have 7, so m squared plus n squared is equal to 0 mod 7, and we want to show m mod 7 is going to be equal to 0, and n mod 7 is also going to be equal to 0. That's what we want to show. So let's look at different numbers, mod 7. So say we had, so I'm going to make a table, 7. So say we had a number mod 1, then we would have the number squared would then be 1 squared, which is equal to 1. If we had mod 7, if we had 2 mod 7, we would have the number squared would leave a remainder of 4. 3 squared, which would be 9, which we can rewrite as being 2 mod 7, since 9 will leave a remainder of 2 when we divide it by 7. 7 or 4 will be 4 squared, which will be 16, which will be 9, which we can then rewrite again as 2. So we continue this list, continue doing this pattern, 5, up until we reach 7. So what you'll note about 7, if you divide 7 by 7, it's going to leave a remainder of 0. So what we can just as well do is we can say this is going to be equal to 0 mod 7, which means that, so 5 is going to be equal to 5 squared, 25, which is equal to 4, 7, 36, 6 squared, and then 36, which mod 7 will be equal to 1. The 0 is going to be 0 squared, which we can rewrite as 0 mod 7. So after 7, there's going to be 8. What you'll notice about 8 is that 8 is also 1 mod 7. So in other words, this case is going to be the same as this case. So we don't even need to consider it. It's going to be the same. And so what we mean by all of this, so I'm going to say This is the possible remainders for m and n divided by 7. And here we have these last few numbers, 1, 4, 2, 2, 4, 1, 0. These were the possible remainders for m squared and n squared divided by 7. So this 1, 4, 2, 2, 4, 1, 0. These are the possible remainders when we are going to divide a square by 7. So these values. So what they tell us is that m squared plus n squared is going to be congruent to 0 mod 7. So we know this is true. And we can rewrite m squared and n squared as being two of these numbers. So what we have to do is we have to choose two of these numbers so that they equal 0, or that they are going to be equal, or that they will be equal to a multiple of 7. So they either need to be equal to 7 or they need to be equal to 0, because they can't be 14 or 21. That would be too big for them. And you'll see that the only option, so that you can add two of them to get to 7, would be 2 zeros. So since m squared plus n squared 7 and squared is equal to 1, 2, 4, 4, 0, and n squared is equal to 1, 2, 4, 4, 0. So one of these options, we've just reduced them since some of them appear twice. The only option would be this is mod 7, sorry. Mod 7 would be for m squared to be 0 mod 7 and n squared to be 0 mod 7 too. So what this means 7 divides m squared, since 7 is a prime. So this means 7 divides m squared and 7 divides n squared. Since 7 is prime, seven is also going to divide m, and 7 is also going to divide n, which is what we wanted to prove. Okay. Now we're going to go on to Euler's totient function. So, I know modular arithmetic may not make sense immediately. You can still ask questions in tomorrow's Q&A, because I know it takes a while to get used to. And once you get used to it, you'll realize that it's actually very useful. Okay, so Euler's totient function, we write it like this. So if we say we read this as phi of n. And what this will be, the number of numbers, wait, let me write rather k, number of integers k in the range 1 kn, for which the GCD of n and k will equal 1. Okay, so let's do an example quickly. Let's look at the number 12. Okay, so let's quickly look at all the numbers below 12. We're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. So if we take, so let's look at the GCD with 12. So GCD of 1 and, so to write GCD with 12. So the GCD of 1 and 12 is going to be 1. The GCD of 2 and 12 is going to be 2. No other bigger factor will, no other bigger divisor will divide both of them. The biggest divisor of 3 and 12 is going to be 3. This will be 4. 5 will be 1. So only 1 divides both 5 and 12. For 6, it will be 6. So 6 divides 6 and divides 12. For 7, it will be 1. For 8, it is going to be 4. For 9, it will be 3. So 3 divides 9 and 3 divides 12. For 10, it will be 2. For 11, it will be 1 again, since nothing except 1 can divide 11 and 12. And then 12, we will have 12 itself. Okay, so let's quickly look at the number of these, how many of these had GCD of 1. So this 1, 2, 3, 4, 5, 6, 7 up to 12, these were the K. So for how many of them was the GCD of 12 and K equal to 1? So this was 1, this was 1, this was 1, and this was 1. So 1, 2, 3, and 4. Which means that this is going to equal 4. Okay. Let's look at another example quickly. So say we had 10. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be K, GCD of 12, 10, and K. So if we have 1 and 10, that's going to be 1. 2 and 10 will be 2. 2 will divide both of them. 3 and 10 will be 1. 4 and 10 will be 2. 5 and 10 will be 5. 6 and 10 will be 2. 7 and 10 will be 1. 8 and 10 will be 4. 9 and 10 will also be 1. 10 and 10 will be 10. So once again, the number of ones, 1, 2, 3, 4. 1, 2, 3, 4. So this answer is also going to be 4. Let's look at the last one. We had 7. Okay, so we have 1, 2, 3, 4, 5, 6, 7. So GCD of 7 and K. So 1 and 7 is going to be 1. 2 and 7 is going to be 1. 3 and 7 is going to be 1. 4 and 7, 1. 5 and 7, 1. 6 and 7, 1. And 7 and 7 is going to be 7. So if you count that up, this will equal 6. So what you'll notice is that for every phi of a prime number, the answer will always be the prime number itself minus 1. Okay, now we have that there's a pretty neat formula for phi of n, which states that if we write n as being P1, alpha 1, P2 for 2, Pk alpha k. So according to the fundamental theorem of arithmetic, P1, P2 up to Pk, they're all prime numbers, unique prime numbers, and alpha 1, alpha 2 up to alpha k are all the exponents. Then we can say that phi of n will equal n times 1 minus 1 over P1, 1 minus P1 over P2, 1 minus P over K. So notice that we don't even include the exponents in this formula. So all you need to know are the prime numbers of n, and then you can work out this formula. So what we had for 7 and for other prime numbers is that if n is prime, then we would have p equal to p 1 minus 1 over p. So it's only going to have one prime divisor. It's going to have itself as the only prime divisor. Then this will equal p minus 1, which will equal p minus 1. So in general, any phi of a prime number is going to be the prime number itself minus 1. So let's use this formula on some of the numbers and see if it works. So say we had phi of 12. So 12 is equal to 2 to the power of 2 times 3. So this is going to equal 12 times 1 minus 1 over 2, 1 minus 1 over 3, which is going to equal 12 times a half times 2/3, which will equal 24 over 6, which is 4. And you'll remember that we got phi of 12 as 4, so this works for 12. We can do something a bit more complicated. So say we had 60. 60 is equal to 2 to the power of 2 times 3 times 5. So this will be equal to 60, 1 minus 1 over 2, 1 minus 1 over 3, and 1 minus 1 over 5. I'm going to erase this, which we can then say is 60, a half, 2/3, and 4/5, which you can then again rewrite as 480 over 30, which will be 16. So there's going to be 16 natural numbers less than 60, which will have a GCD of 1 when you compare it to 60. Okay, now we're going to use a formula that combines the totient function and modular arithmetic, and we call this the Euler-5 function, Euler-5 theorem, sorry. Or we can say Fermat's okay. So the first one, Euler-5 theorem, says that if you have an integer a and you have the a to the power of phi of n, then we are going to have that this is going to equal 1 to 1 mod n, where GCD of a and n are equal to 1. So remember we had that if phi of a prime is p is going to be p minus 1. So if n is a prime, phi of a prime is going to be p minus 1 mod p, is then going to equal 1. So this is Fermat's little theorem. So also GCD AP equals to 1. So let's look at an example. Say we had 57 as being A, and we take this n as being 11, then phi of 11, since 11 is a prime, phi of 11 is going to be 10, so this will be equal to 1. You can also take 97 as A, n is equal to 12 then. We had phi of 12 is equal to 4, so 97 to the power of 4 is going to equal 1, or more. It's going to be congruent to 1 over 12. Okay, so let's do another problem involving this. Okay. So this problem says that find the least positive integer k such that 2050 to the power of 2051 can be written as a sum of k fifth powers. So firstly, let's look at Fermat's little theorem. So Fermat's little theorem says so we're going to take P is equal to 11. Then we will have a to the power of 10 is 11, so 1. So for all a part of the integers, where the GCD of a and 11 is 1. So in this case, okay, now we can rewrite a to the power of 10 is going to be equal to a to the power of 5 squared, which mod 11 will be 1, which we had over here, which means that 11 is going to divide a to the power of 5 to the power of 2 minus 1. So we take the 1 over, and then there will be a 0 on this side, which means 11 will divide the term on the left-hand side. We can then rewrite this side again as being a to the power of 5 minus 1 times a to the power of 5 plus 1. So it's difference of squares again. Difference of squares. So this means 11 divides a to the power of 5 minus 1, or 11 divides a to the power of 5 plus 1. So writing this over again in modular arithmetic, we have that a to the power of 5 is congruent to 1 mod 11, or we have that a to the power of 5 is congruent to minus 1, 11. So now we already have the two options for a to the power of 5. The remainder when it is divided by 11 is going to be 1 or minus 1. Now we should remember that when we applied Fermat's law theorem, we assumed that the GCD of a and 11 is equal to 1. So if GCD of a and 11 is not 1, then this means that 11 will divide a. So a and 11 will then have a common divisor, and since 11 is a prime factor, this means the only option this is possible, the only way this is possible is if a will also be divisible by 11. Okay, so now we have all the options. This means, let's rewrite this in modular arithmetic as well. So this will mean a to the power of, or a mod 11 will be equal to 0, which means a to the power of 5 is going to be 0 to the power of 5, which is equal to 0. Okay, so this means a to the power of 5 mod 11 is going to be minus 1, or 0, or 1. So either it's going to be minus 1, or it's going to be 1, or it's going to be equal to 0. One of these three options. So the reason we took a to the power of 10 is because we wanted to get this a to the power of 5. And why did we want to get this a to the power of 5? We wanted to get this a to the power of 5 since the question mentions fifth powers. So we want to see, we want to do something with this fifth powers and maybe reduce it to something smaller or deduce something useful from it. So let's look at the original number again. So they asked for 2050 to the power of 2051, which is equal to 2050 to the power of 25 times 10 times 2050. So just using basic exponent rules, so 205 times 10 plus 1 is going to equal 2051. And okay, so we have 2050. Let's rewrite 2050 in terms of its remainders. So 2015 mod 11 is going to be 4. By Fermat's law theorem, we also had that, so we had a to the power of 10, 1, if GCD A11 is 1. So since GCD of 2050 and 11 is 1, so we had that 2050 does not divide 11, it's going to leave a remainder of 4. So 2050 then we can say that 2050 to the power of 10 is going to be equal to 1 mod 11. So we can actually switch these exponents, so these would be 10, 205, so 2050, writing this over again, 2051 equal to 2050 and 5, 205, 1. then this mod 11 is going to be 1 times to the power of 2 over 5 times 4, which will just be equal to 1 times 4, so this will be equal to 4. So we know 20, so we know (2050) to the power of 2051 is going to be some k1 to the power of 5 plus some k1, let me write another number, so some alpha 1 to the power of, let me write it as b, some b1 to the power of 5 plus b2 to the power of 5, on and on and on for k stuff. So we want to minimize this k, that's what the question asks. So we know all of these, so mod 11, this is going to be equal to 4, and we have deduced that the options for these to the power of 5 are going to be 0, 1, or minus 1, plus 0, 1, minus 1, plus 0, 1, minus 1, on and on, until the last one has been reached. So we had the remainder is going to be minus 1, 0, 1. So now we have, these are going to be, these b to the power of 5 are going to be either one of these, are going to be either 0, 1, or minus 1, and these have to add up to 4. So the minimum value of b's are going to be 4. So minimum number of b's are going to be 4, so that we can say 1 plus 1 plus 1 plus 1 will equal 4. So we now say we want to prove k equals 4 is the minimum solution. Okay. Now what we do is we find a solution to this. So there's a few solutions to this if I remember correctly, but the one the memo gives is as follows. So b1 equal to 2050 401 times 2, b2 2050 401 times 2, b3 2050 401, and then b3 b4 2050 401. So you'd get this by experimenting a bit and trying to divide the original number 2050 to the power of 2051 and try to see if there are any numbers that you can take out and rewrite. So I know this question may be a bit confusing, especially if you're not quite used to modular arithmetic, so don't worry if you didn't understand everything. You're welcome to ask me if there was a part that didn't make sense, which I'm sure you got a bit confused at some point. Also notice that even though we found that k equals 4 is a option, this doesn't mean it was necessarily the correct answer. So we had to prove that there was some construction. So there did actually exist some numbers so that you could take the fifth powers and the question could be true. Okay, so thank you for listening today. I'm sorry if this was a bit confusing. You're welcome to ask more questions in the Q&A. Okay, see you tomorrow.